Hi everyone, I am Ignacio Araya and I am a faculty member at Universidad Arturo Prat. Today I will be presenting about obtaining Einstein gravity from conformal gravity in 6 dimensions. So first I will present the theory, what is conformal gravity and some of its properties. Then I will mention how in the case of 4 dimensions it is possible to obtain Einstein gravity by imposing certain conditions on the Weyl tensor. And then I will talk about conformal gravity in 6 dimensions and how the same idea can be extended in the 6-dimensional case. So first of all, conformal gravity as a theory, right, was proposed by Hermann Weyl in 1919. And it is essentially Weyl squared gravity, so it's a type of higher curvature gravity. And the action principle is just the square of the Weyl tensor, and it has a Weyl symmetry, so namely a local rescaling symmetry of the metric. So the equation of motion for the theory obtained after varying the action, right, corresponds to the Bach flat condition, namely the vanishing of the Bach tensor, which is defined in equation 2. Now, in order to implement this condition, the definitions of the Cotton, Schouten, and Weyl tensors are given in equations 3 to 5. And an interesting point is that in the case of Einstein spacetimes, the Schouten tensor becomes a constant, and therefore the Cotton is identically 0. And also the Weyl tensor simplifies in just the Riemann tensor plus a constant term, and therefore it can be shown that the Bach is identically 0 for any Einstein spaces. So what is an Einstein space? The Einstein condition can be understood in different ways. The most usual one is just to consider that the Einstein tensor is equal to 0, but one can also recast the Einstein condition in terms of the vanishing of the traceless part of the Ricci tensor, which is defined in equation 6. So imposing the traceless Ricci to be identically 0 is equivalent to imposing the Einstein equation. The interesting thing is that, as mentioned before, condition 6 fixes a constant form for the Schouten, and it also implies that the Cotton and the Bach are 0. And furthermore, the Ricci tensor is related directly to the Weyl in the Einstein case, such that the Weyl tensor becomes simply a constant displacement of the Riemann tensor. And furthermore, the Ricci scalar is also fixed to a constant. Considering these conditions and definitions of the tensors, the action of conformal gravity, which is just Weyl squared, can be rewritten in terms of the ADS curvature tensor F and the traceless part of the Ricci tensor, as shown in equation 8. Now, imposing an Einstein condition on the spacetime is equivalent to requiring h equals to 0. And also, because in the Einstein case, the Ricci scalar is just a constant, the action simplifies into equation 9. This equation 9 corresponds to a McDowell-Mansouri form for the Einstein-Hilbert action, which can be opened and rewritten as in equation 10. And as you can see, the action in equation 10 is simply the usual Einstein-Hilbert action in an ADS space, so namely a space with a negative cosmological constant, plus a topological term, which is the Gauss-Bonnet, that has no dynamics. So as it turns out, equation 10 is dynamically equivalent to Einstein gravity, and furthermore, it has the addition of a topological term, which renders the action finite. So it is renormalized Einstein gravity. So now, this basically shows that the theory of conformal gravity in 4 dimensions is equivalent to Einstein gravity when evaluated on Einstein spacetimes, considering spaces of asymptotically ADS form. This means spacetimes that have negative cosmological constant. Of course, this may not be directly relevant for our universe. However, it is important in the context of ADS-CFT where spaces with ADS asymptotics are taken as a mathematical tool in order to do computations for CFTs. Now, as it turns out, in 6 dimensions, the same feature of being able to obtain Einstein gravity from conformal gravity holds. In this case, there are 3 linearly independent conformal invariants. So instead of just having one, namely the Weil squared, as in the 4D case, here you can have a space of possible theories for different linear combinations of these conformal invariants. So in principle, any of such linear combinations defines a conformal gravity. However, there is a unique combination that has an Einstein sector. This combination was studied by Lupang and Pope, and it was found that for a particular combination of the couplings, given in equation 14, the resulting theory admits a Schwarzschild ADS black hole solution, and therefore, more generally, it has an Einstein sector. As it turns out, that particular definition of conformal gravity can in turn be rewritten in terms of the Weil, Cotton, and Schouten tensors, which, as shown previously for the 4-dimensional case, is a very important definition because it allows to implement the Einstein condition with ease. Doing this, the Lupang and Pope conformal gravity can be rewritten as in equation 15. And then it is easy to show that for Einstein spaces, which satisfy the vanishing of the Cotton, and also the fact that the Schouten tensor is a constant, and that the Weil tensor is simply the ADS curvature, which, as we had explained before, is the Riemannian curvature plus a constant displacement. This action becomes a polynomial in the ADS curvature, plus a certain boundary term. And as I will show in the next slide, this expression corresponds to the Einstein gravity action for spacetimes with ADS asymptotics in 6 dimensions. In order to show this explicitly, the same action can be decomposed in terms of the Einstein parts given in terms of the ADS curvature tensor, and a functional of the traceless Ricci tensor, which identically vanishes for Einstein manifolds. The polynomial in F is given by expression 17, and when choosing a particular value of the overall factor in the action, it turns out that the action 16, when imposing the Einstein condition, namely the vanishing of the traceless Ricci, can be rewritten as equation 18. Now, equation 18 can be directly shown to be Einstein gravity with negative cosmological constant, plus a topological invariant, which is the Euler 6, and a boundary term. So this action is dynamically equivalent to Einstein gravity, and furthermore, the coupling of the topological term and the boundary term make it so that the action is finite, and therefore it results in renormalized Einstein gravity. And as a summary, conformal gravity in 4 dimensions and 6 dimensions can be defined as a combination of the conformal invariants, which is the unique combination that has an Einstein sector in solution space. In 4 dimensions, this is guaranteed because there is only one possible conformal invariant, the Weil squared. However, in 6 dimensions, that constrains the theory to the one that I previously shown. Any Einstein ADS manifold is also a solution of the theory. This is shown because the equation of motion obtained by varying the action vanishes identically when the Einstein condition is implemented, namely the vanishing of the Cotton and the fact that the Schouten is a constant and that the Weil becomes directly the ADS curvature. The action of conformal gravity can be reduced to that of topologically normalized Einstein ADS gravity when imposing the Einstein condition on the manifold, as shown before, both in 4D and 6D cases. And finally, the Einstein condition is understood holographically as imposing generalized Neumann boundary conditions on the metric at the conformal boundary. This is an extension of Maldacena's argument in 4 dimensions. Thank you very much.